Hello there, and welcome. I'm Matthew Gray, and I'm grateful you've chosen to spend this time here tonight. Right now, wherever you are beneath this vast sky, let this moment be yours. Let the day's weight lift away. Let the urgency fade into something gentler, something that asks nothing of you. Tonight, we're not staying grounded on one world. We're drifting outward, into the neighborhood we call home. Our solar system is more intricate, more balanced, and more astonishing than most of us ever pause to consider. From the molten fury of Mercury to the icy whispers at the edge of the Kuiper Belt, from moons that hide oceans beneath frozen shells, to rings that dance in perfect mathematical harmony, this cosmic family moves together in ways that will quiet your mind, soften your breathing, and remind you that you are part of something ancient and beautiful. We are passengers on a planet that is itself a passenger, orbiting a star that is orbiting the center of a galaxy. All of us moving through space in patterns set in motion long before consciousness emerged to wonder at them. Some of what you hear tonight might shift how you see that point of light in the evening sky. Other moments will simply drift past like dust motes in a sunbeam, gentle and unhurried and quietly unforgettable. If you find value in this journey through our cosmic neighborhood, please consider liking this video and subscribing to the channel. It helps others discover this quiet space we're creating together. Take a deep breath and let's begin this slow journey through the quiet wonders of our solar system. The sun sits at the center of everything we know, and it's been burning for 4.5 billion years. Every second, it converts 600 million tons of hydrogen into helium through nuclear fusion deep in its core, where temperatures reach 27 million degrees Fahrenheit. This process releases energy that takes thousands of years to travel from the core to the surface, bouncing around through dense layers of plasma like a photon pinball game. Once it reaches the surface, that same energy takes just 8 minutes to cross the void and reach us here. The light touching your skin right now began its journey in the heart of a star long before you were born, working its way outward through impossible heat and pressure before finally escaping into space. The sun is not eternal, though it feels that way to us. In another 5 billion years, it will exhaust its hydrogen fuel and begin fusing helium instead, swelling into a red giant that may consume Mercury, Venus, and possibly Earth. The outer layers will drift away, creating a planetary nebula, while the core collapses into a white dwarf, slowly cooling over trillions of years. But for now, it burns steadily, providing the energy powering every living thing on our world. Without this star, Earth would be frozen solid, temperatures plunging to near absolute zero. The oceans turned to ice, the atmosphere frozen on the ground. We are children of the sun in the most literal sense. Made from atoms it helped create, and sustained by energy it provides every moment without pause. And as the light from this ancient furnace streams outward at 186,000 miles per second, it first encounters the planet closest to its embrace. Mercury orbits the sun every 88 Earth days, spinning so slowly that a single day from sunrise to sunrise lasts 176 Earth days. This creates a situation where one Mercurian year passes faster than 2 of its days. If you stood on the surface, you'd watch the sun crawl across the sky at an agonizingly slow pace, sometimes appearing to move backward in apparent retrograde motion caused by the planet's elliptical orbit changing its speed. The sun would stop, reverse briefly, then continue forward across the black sky. Temperature swings on this airless world are the most extreme of any planet. The side facing, the sun reaches 800 degrees Fahrenheit, hot enough to melt lead and zinc. The night side plunges to minus 290 degrees, with no atmosphere to distribute heat. The boundary between day and night is a harsh line where temperatures drop over 1,000 degrees within a short distance. Despite being closest to the sun, Mercury harbours water ice in permanently shadowed craters at its poles. These craters never receive direct sunlight due to the planet's nearly zero axial tilt, staying cold enough for water ice to persist indefinitely. This ice was likely delivered by ancient comets. The surface is heavily cratered, a record of ancient bombardment. One impact, the Caloris Basin, sent shockwaves around the entire planet, creating jumbled terrain on the exact opposite side. It's a scar frozen in time, showing what the early solar system was like when collisions shaped every world. Venus is Earth's twin in size, but utterly different in character. Its atmosphere is 92 times thicker than ours, creating surface pressures equivalent to being 3,000 feet underwater. That atmosphere is 96% carbon dioxide, creating a runaway greenhouse effect, making it the hottest planet in the solar system at 900 degrees Fahrenheit. This makes it hotter than Mercury, despite being nearly twice as far from the sun. The clouds aren't water vapor, but sulfuric acid, raining down but evaporating before reaching the surface. These clouds reflect most sunlight, making Venus the brightest planet in our sky, visible even in daylight. Venus rotates backward, and so slowly that one day, 243 Earth days, is longer than its year. 225 Earth days. The sun rises in the west and sets in the east, if you could see it through the thick yellowish haze. Scientists believe Venus wasn't always this hostile. Early in its history, it may have had liquid water oceans and moderate climate. But something went wrong. Perhaps volcanic activity released too much carbon dioxide. Perhaps it lost its magnetic field, allowing solar wind to strip away its water. Whatever the cause, it transformed from potential paradise into hellscape. Yet high in its atmosphere, about 30 miles up, temperatures and pressures are surprisingly Earth-like. Some scientists speculate that microbial life could exist there, floating in clouds, never touching the infernal surface below. It's a tantalizing possibility. Life persisting above a world that became uninhabitable. Earth is the only planet where water exists simultaneously in all three states on its surface: solid ice, liquid water, and gaseous vapor. This drives weather systems, erosion, and the water cycle. We orbit in the habitable zone, not too close to the sun and not too far, positioned perfectly for liquid water to persist over billions of years. Our atmosphere is unusual, 78% nitrogen and 21% oxygen. That oxygen is not natural without life. Before photosynthetic organisms evolved, Earth's atmosphere had almost no free oxygen. Ancient microbes transformed the air over billions of years, releasing oxygen as waste. This great oxygenation event, about 2.5 billion years ago, created the atmosphere we breathe. We live inside an atmosphere created and maintained by life itself. The planet's magnetic field, generated by churning liquid iron in the outer core, shields us from solar wind. Without this barrier, particles from the Sun would strip away our atmosphere over millions of years, as happened on Mars. This field also creates auroras, shimmering curtains of light near the poles where particles funnel down magnetic field lines. We orbit at 93 million miles from the Sun, a distance called an astronomical unit. Light takes 8 minutes 20 seconds to reach us, meaning we see our star not as it is now, but as it was 8 minutes ago. We are always looking at the past when we look at the sky. Mars is half Earth's diameter, with a day remarkably similar to ours at 24 hours 37 minutes. From its surface, the sky during the day is butterscotch coloured, caused by dust suspended in the thin atmosphere. At sunset, the sky around the Sun glows blue, opposite our sunsets, because dust particles scatter light differently. Mars once flowed with water. Evidence is everywhere: dry riverbeds, minerals forming only in water, layered sediments telling stories of ancient shorelines. Scientists estimate it may have had an ocean covering its northern hemisphere billions of years ago. But something changed. The leading theory is Mars lost its magnetic field, allowing solar wind to strip away its atmosphere gradually. Without that protection, and without volcanic activity to replenish gases, the air thinned until water could no longer exist as liquid. Today, the atmosphere is less than 1% as thick as Earth's, but water is still there, locked in polar ice and underground. Recent discoveries show liquid water likely exists in subsurface lakes beneath ice caps. If life emerged during Mars's wetter past, it might persist in these refuges. The surface features Olympus Mons, the largest volcano in the solar system, rising 72,000 feet, nearly 3 times Everest's height. It formed because Mars lacks plate tectonics, so volcanic hotspots stayed in place, building higher over millions of years. Valles Marineris stretches over 2,500 miles long and 4 miles deep, dwarfing the Grand Canyon. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, ranging from dust to objects hundreds of miles across. These fragments never coalesced into a planet because Jupiter's gravity kept stirring them up, preventing stable orbits where they could merge. Instead, Jupiter increased collision speeds, causing asteroids to shatter rather than stick together. Despite movie depictions, the belt is mostly empty space. Flying through it, you'd likely pass without seeing a single asteroid up close. They're separated by millions of miles, each essentially alone. The largest object, Ceres, is massive enough to be a dwarf planet. With a diameter of 584 miles, it contains nearly a third of the belt's total mass. Recent observations revealed it likely harbours a subsurface ocean beneath its icy crust, kept liquid by heat from radioactive decay. Bright spots on its surface are salt deposits where briny water reached the surface and evaporated. Some asteroids are made almost entirely of metal, primarily iron and nickel, exposed cores of larger bodies shattered by collisions. These metallic asteroids offer glimpses into planetary cores normally hidden deep underground. Occasionally, asteroids wander out of the belt, their orbits perturbed by Jupiter. Some cross Earth's orbit, becoming near-Earth objects we track carefully. The asteroid that struck 66 million years ago was only 6 miles across, but released energy equivalent to 10 billion nuclear bombs, ending the age of dinosaurs. Jupiter contains more than twice the mass of all other planets combined. It's a gas giant without solid surface, composed mostly of hydrogen and helium. If you descended through its atmosphere, you'd pass through cloud layers, then regions where gas becomes denser until pressure transforms hydrogen into liquid, then deeper still into metallic hydrogen conducting electricity. At the center lies a core, possibly rock and metal, under such extreme pressure it might be dissolved into surrounding hydrogen. The Great Red Spot is a storm larger than Earth, raging for at least 400 years. Winds reach 280 miles per hour, and the structure rotates counterclockwise, a hurricane never making landfall. It's been shrinking for over a century for reasons not fully understood, though it remains enormous. Jupiter rotates faster than any other planet, completing one spin in 9 hours 55 minutes. This rapid rotation flattens it noticeably, making it wider at the equator than pole to pole by 7%. The spin creates powerful winds, organized into alternating dark belts and light zones wrapping the planet. These bands move at different speeds, creating shear zones where winds reach hundreds of miles per hour. Jupiter acts as gravitational shield for inner planets, its massive bulk attracting comets and asteroids, either capturing them or deflecting them away. Without Jupiter's protection, Earth would be struck far more frequently by large objects from the outer system. Io is the most volcanically active body in the solar system, its surface constantly resurfaced by eruptions. It's caught in gravitational tug-of-war between Jupiter and other large moons, particularly Europa. This squeezing and stretching generates internal heat, keeping its interior molten despite being far from the sun. Plumes of sulfur erupt hundreds of miles into space, falling back to coat the surface in yellows, reds, and blacks. There's no water on Io, only rock, sulfur, and lava. Watching from a spacecraft, you'd see eruptions in real time, geysers of molten material arcing into black sky. It's a world too tortured by gravity to be peaceful. Europa is slightly smaller than our moon, with a surface of water, ice, crisscrossed by cracks and ridges. Beneath this frozen crust lies an ocean perhaps 60 miles deep, containing more water than all Earth's oceans combined. Evidence comes from magnetic measurements showing something electrically conductive beneath the ice, and from how the surface shifts, suggesting it floats on liquid below. The ocean is kept liquid by tidal heating, as Europa orbits Jupiter in an elliptical path, getting squeezed and flexed, generating heat through friction. Where there's liquid water and energy, there's potential for life. Europa has both, possibly with chemicals from the rocky seafloor, creating conditions similar to Earth's hydrothermal vents, where life thrives in darkness. The ice shell is estimated to be 10 to 15 miles thick, a barrier between us and the ocean below. Future missions might drill through and send submarines into the ocean to search for life. Ganymede is the largest moon in the solar system, bigger than Mercury, with its own magnetic field. Its surface is a mix of dark, ancient terrain and lighter grooved regions where ice has been stretched and fractured by tectonic forces. Like Europa, it likely has a subsurface ocean beneath 100 miles of ice and rock, detected through magnetic measurements. The surface is heavily cratered in dark regions, recording billions of years of impacts, while grooved terrain is younger, perhaps only 1 billion years old. This suggests Ganymede went through a period of resurfacing before cooling and quieting. Standing there, you'd see Jupiter dominating the sky, nearly 10 times wider than the moon appears from Earth. and you'd notice your weight is just 1/7 normal. Callisto is the most heavily cratered object in the solar system, its surface saturated with impacts. There's almost no room for new craters without overlapping old ones, suggesting the surface is incredibly ancient, perhaps 4 billion years old. Unlike other large moons, Callisto shows little geological activity. It may have a subsurface ocean, but if so, it's isolated by thick ice and rock. It orbits far enough from Jupiter to avoid intense tidal heating, so it remains cold, quiet, and static. This makes it less interesting for astrobiology, but useful for future exploration. Its stable surface would make a good base for missions to the Jupiter system. Saturn is perhaps the most beautiful planet, known for its rings more than anything else. These rings are made of countless ice and rock particles, ranging from grains to house-sized boulders, all orbiting in a flat disk. They're surprisingly thin, sometimes only 30 feet thick, though extending hundreds of thousands of miles. The rings aren't solid, but individual particles, each a tiny moon orbiting independently. They collide gently, occasionally breaking or sticking together, constantly evolving. Some gaps are cleared by small shepherd moons, whose gravity sweeps particles away. We don't know how old the rings are. They might be ancient or relatively young, perhaps created when a moon wandered too close and was torn apart by tidal forces. Evidence suggests they might be only a few 100 million years old, meaning they may not be permanent and could eventually spread out and disappear. Saturn itself is similar to Jupiter, a gas giant made mostly of hydrogen and helium with no solid surface. It spins rapidly, taking only 10.5 hours to rotate, creating bands of clouds and powerful winds. Its atmosphere is calmer than Jupiter's without dramatic storms, though occasionally massive storms erupt. The planet's density is less than water. If you found an ocean large enough, Saturn would float. Titan is Saturn's largest moon and the second largest in the solar system. It's the only moon with a thick atmosphere, denser than Earth's, made mostly of nitrogen with methane. This atmosphere is so thick it hides the surface completely, creating an orange haze. Beneath that haze lies a landscape strangely Earth-like. There are lakes and rivers filled with liquid methane and ethane. It rains methane, forming puddles and streams, carving channels through icy terrain. There are mountains, possibly made of water ice, which at Titan's frigid temperatures is as hard as rock. The surface temperature is -290 degrees Fahrenheit, far too cold for liquid water. But Titan has organic chemistry, complex carbon-based molecules raining from the atmosphere and accumulating on the surface. These are building blocks of life as we know it, though Titan is too cold for life like ours. Some scientists speculate that if life exists there, it would be radically different, perhaps using liquid methane as solvent instead of water. A lander called Huygens descended through Titan's atmosphere in 2005, sending back images of a surface with rounded rocks scattered across a plain, shaped by flowing liquids. Enceladus is small, only 300 miles across, but incredibly intriguing. Its surface is bright white ice, highly reflective, making it one of the most reflective bodies we know. That brightness comes from fresh ice, constantly replenished by geysers erupting from cracks at the South Pole. These geysers shoot water vapor and ice particles hundreds of miles into space. Some material falls back, coating the surface, while some escapes to form a faint ring around Saturn. The water comes from a subsurface ocean, perhaps 6 miles deep, beneath 10 miles of ice. Spacecraft have flown through the plumes, analyzing their composition, finding not just water, but organic molecules, salts, and hydrogen gas, indicating chemical reactions between water and rock. These are conditions needed for life, similar to Earth's hydrothermal vents. The heat keeping the ocean liquid likely comes from tidal heating, though Enceladus is small and shouldn't have enough internal heat. The fact it does suggests its interior is more active than expected. Uranus is tipped on its side, rotating at 98 degrees, meaning its poles point almost directly at the Sun at different times in its orbit. This gives extreme seasons. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. No one knows why it's tilted so dramatically. The most likely explanation is a massive collision early in its history knocked it sideways. It's an ice giant, not a gas giant, meaning its interior is mostly water, methane, and ammonia ices, rather than hydrogen and helium. Its atmosphere is calm with few visible storms, giving it a featureless blue-green appearance due to methane absorbing red light. It has faint rings discovered only in 1977, much darker and narrower than Saturn's. These rings are made of dark particles, possibly organic material, difficult to see even with powerful telescopes. Neptune is the farthest planet, orbiting where sunlight is 900 times dimmer than on Earth. Despite this, it's surprisingly dynamic, with the strongest winds in the solar system reaching 1,200 miles per hour. These winds drive massive storms, including the Great Dark Spot, similar to Jupiter's Great Red Spot, though less permanent. The planet's blue color comes from methane in its atmosphere absorbing red light and reflecting blue. It's a deeper, richer blue than Uranus, and the atmosphere shows more structure with streaks, bands, and occasional bright clouds made of methane ice crystals. Neptune has 14 known moons, the largest being Triton. This moon is unusual because it orbits backward, suggesting it wasn't formed alongside Neptune, but was captured, likely a dwarf planet from the Kuiper Belt that wandered too close. Triton's surface is young, covered in nitrogen ice, and it has geysers erupting nitrogen gas. Triton is slowly spiraling inward, pulled by Neptune's gravity. In a few billion years, it will be torn apart by tidal forces, creating a spectacular ring system. The Kuiper Belt extends from Neptune's orbit out to about 50 astronomical units, a vast region of icy bodies left from the solar system's formation. These objects are too far from the Sun to have coalesced into planets, remaining as frozen remnants. Pluto is the most famous Kuiper Belt object, once called a planet, now classified as dwarf planet after similar-sized objects were discovered. It has a heart-shaped region of nitrogen ice on its surface, mountains made of water ice, and an atmosphere that freezes and falls as snow when Pluto moves farther from the Sun. Pluto has 5 known moons, the largest being Charon, so large relative to Pluto that they orbit a common center of mass between them. This makes them almost a binary system, 2 worlds locked in gravitational dance, each always showing the same face to the other. Other Kuiper Belt objects include Eris, slightly smaller than Pluto, but more massive, and Haumea, a rapidly spinning object stretched into an egg shape. Comets are icy bodies from the outer reaches, sometimes venturing inward toward the Sun. As they approach, the Sun's heat causes their ices to sublimate, turning directly from solid to gas, creating a glowing coma and often a tail stretching for millions of miles. These tails always point away from the sun, pushed by solar wind. Most comets come from two regions, the Kuiper belt and the Oort cloud. The Oort cloud is a theoretical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. Objects there orbit so slowly, they take millions of years to complete one orbit. They're so distant that passing stars can occasionally perturb them, sending them falling inward. Some comets have been visited by spacecraft, revealing surfaces covered in dust and organic molecules with jets of gas erupting from specific locations. The sun's influence extends far beyond the planets. The solar wind, a stream of charged particles flowing outward, fills space between worlds, creating a bubble called the heliosphere. This bubble protects the solar system from the interstellar medium, the thin gas and dust between stars. The edge, called the heliopause, is where solar wind meets interstellar medium and slows down. Two spacecraft, Voyager 1 and Voyager 2, have crossed this boundary, becoming the first human-made objects to enter interstellar space. Beyond the heliopause lies true interstellar space, vast distances where stars are light years apart. From there, looking back, the sun would appear as just another star. Nothing special, one light among countless others. But to us, it's everything. It's home, the center around which our lives orbit. Our moon is Earth's only natural satellite, and it's unusually large compared to its parent planet. Most moons in the solar system are tiny compared to their planets, but our moon is over a quarter of Earth's diameter. This size ratio is so unusual that Earth and the moon are sometimes considered a double planet system, rather than a planet-moon system. The moon formed about 4.5 billion years ago, shortly after Earth itself, likely from debris ejected when a Mars-sized object collided with the young Earth. This giant impact threw molten material into orbit, which gradually coalesced into the moon. Evidence for this theory comes from the moon's composition, which closely matches Earth's outer layers, and from computer simulations showing such a collision could produce exactly what we observe. The moon has no atmosphere, which means there's no wind, no weather, no erosion. Footprints left by Apollo astronauts in 1969 remain unchanged and will persist for millions of years. The lack of atmosphere also creates extreme temperature swings, from 260 degrees Fahrenheit during the lunar day to minus 280 degrees during the lunar night. The moon is tidally locked to Earth, meaning the same side always faces us. This happened because Earth's gravity created tidal bulges in the moon early in its history, and friction from these bulges gradually slowed its rotation until it matched its orbital period. The far side, often incorrectly called the dark side, gets just as much sunlight as the near side, but we never see it from Earth. Phobos and Deimos, Mars's two small moons, are likely captured asteroids, rather than moons that formed alongside the planet. They're irregularly shaped, heavily cratered, and quite small. Phobos, the larger of the two, is only about 17 miles across. It orbits so close to Mars, just 3,700 miles above the surface, that it completes 3 orbits every Martian day. This proximity means Phobos is slowly spiraling inward, pulled by tidal forces. In about 50 million years, it will either crash into Mars or be torn apart by tidal forces, creating a ring system around the planet. Deimos is smaller and orbits farther out. about 14,000 miles above the surface. From the Martian surface, Phobos would appear to move across the sky from west to east, opposite the Sun's motion, because it orbits faster than Mars rotates. Deimos, orbiting more slowly, would rise in the east and set in the west like the Sun, but it would take about 2.5 days to cross the sky. Both moons are dark, reflecting only about 7% of the light that strikes them, making them difficult to see even though they're close. Their composition suggests they're made of carbon-rich rock similar to certain types of asteroids found in the outer asteroid belt, supporting the theory that they were captured by Mars's gravity early in the solar system's history. Orbital mechanics follow simple laws discovered by Johannes Kepler in the early 1600s. Objects in orbit move in ellipses, not perfect circles, with the object they're orbiting at one focus of the ellipse. They move faster when closer to the object and slower when farther away. A line drawn from the orbiting object to the object it orbits sweeps out equal areas in equal times, meaning if you track the orbit over time, the area covered in any given period is constant, and the square of an orbital period is proportional to the cube of the average orbital distance, a relationship allowing us to calculate orbital periods for any distance. These laws seem abstract, but they govern everything in the solar system, from planets orbiting the Sun, to moons orbiting planets, to spacecraft orbiting Earth. They're the reason satellites stay in orbit rather than falling, the reason we can predict exactly where planets will be centuries from now, and the reason space missions can navigate across millions of miles with incredible precision. There's something deeply satisfying about the predictability of orbital mechanics. The way objects move along paths determined billions of years ago. Paths they'll continue to follow until something disturbs them. It's a clockwork universe at this scale, each piece moving according to rules that never change, creating a stability that spans eons. Volcanic eruptions on Io are driven not by radioactive decay like Earth's volcanism, but by tidal heating. As Io orbits Jupiter in an elliptical path influenced by Europa and Ganymede, it gets squeezed and stretched like a rubber ball. This constant flexing generates friction inside the Moon, producing enough heat to keep the interior molten. The result is over 400 active volcanoes covering the surface, making Io the most volcanically active body we know. Unlike Earth's volcanoes that erupt molten rock, some of Io's volcanoes erupt liquid sulfur and sulfur dioxide gas. Sulfur on Io exists in several different forms depending on temperature, each with a different color, ranging from yellow to red to black. This gives the Moon its distinctive appearance, looking like a cosmic pizza with splotches of different colors covering the surface. Plumes from these eruptions can reach heights of 300 miles, far higher than any volcanic plume on Earth, because Io's low gravity and lack of atmosphere allow material to travel much farther before falling back down. Some of this material achieves escape velocity and forms a torus, a donut-shaped cloud of charged particles surrounding Jupiter along Io's orbit. This torus interacts with Jupiter's magnetic field, creating electrical currents that generate radio emissions detectable from Earth, linking Io and Jupiter in an electromagnetic dance visible across the solar system. Enceladus's geysers create intricate patterns on its surface called tiger stripes, long parallel cracks in the south polar region where the ice is warmest and most active. These stripes are warmer than surrounding terrain, reaching minus 120 degrees Fahrenheit compared to minus 330 degrees elsewhere. Temperatures might seem uniformly cold to us, but this difference is significant enough to keep water liquid just beneath the surface in the stripes. The stripes are about 80 miles long and only a mile wide, precise fractures where the ice shell is thinnest. Material from the subsurface ocean finds its way through these cracks and erupts into space. The ice particles in these eruptions are tiny, microscopic crystals that catch sunlight and create a faint haze around the moon. Some particles are large enough to fall back to the surface under Enceladus's weak gravity, while others achieve escape velocity and join Saturn's E-ring, a faint ring aligned with Enceladus's orbit, made almost entirely of ice particles from these geysers. The geysers aren't constant, but vary in intensity, possibly controlled by tidal forces as Enceladus orbits Saturn. When the moon is farthest from Saturn, the cracks widen slightly, and the geysers become more active. When it's closest, the cracks compress, and activity decreases. This creates a rhythmic pattern, a breathing cycle synchronized with the orbit, as if the moon is alive in some fundamental way. Saturn's atmosphere has occasional outbursts called great white spots, enormous storms that erupt roughly once every 30 years, though the timing isn't perfectly regular. These storms are bright enough to be seen from Earth through modest telescopes, appearing as pale ovals against Saturn's usual banded appearance. They can grow to encompass areas larger than Earth, with wind speeds exceeding 1,000 miles per hour. The storms seem to originate deep in Saturn's atmosphere, where temperatures and pressures are much higher than at the visible cloud tops. Something triggers convection, hot material rising rapidly, creating turbulence that manifests as a bright storm at the cloud level. The storms eventually spread out, carried by Saturn's strong east-west winds, wrapping around the entire planet in a bright band before gradually fading over months. The most recent great white spot occurred in 2010, appearing in Saturn's northern hemisphere and lasting for about 8 months. Observations from spacecraft and ground-based telescopes revealed it disturbed the atmosphere down to depths of at least 200 miles, showing how deep and powerful these storms really are. Why they occur roughly every 30 years remains unclear. One possibility is that they're related to Saturn's seasons, which last about 7 years, each since Saturn takes 29.5 years to orbit the Sun. Perhaps something about the seasonal changes in sunlight distribution triggers conditions favorable for these massive eruptions. Uranus experiences the most extreme seasons of any planet due to its 98-degree axial tilt. When one pole points toward the Sun, that entire hemisphere experiences continuous daylight for 42 years, while the opposite hemisphere endures continuous night. Then, as Uranus continues its orbit, the equatorial regions get their turn for direct sunlight during the planet's brief spring and autumn, each lasting about 21 years. Finally, the previously dark pole points toward the Sun, and the seasons reverse. This means if you lived on Uranus's North Pole, you'd experience 42 years of summer, with the Sun circling the horizon without setting, followed by 42 years of winter in total darkness. A day-night cycle measured in decades rather than hours. Despite these extreme seasonal changes, Uranus's atmosphere doesn't show dramatic variations between seasons. Scientists expected the summer pole to be much warmer than the winter pole, but observations show temperatures are surprisingly uniform across the planet. Heat must be redistributed from the summer to winter hemisphere somehow, perhaps by atmospheric circulation patterns we don't fully understand yet. This temperature uniformity makes Uranus puzzling. It should show more dramatic differences, but instead it remains calm, almost featureless, revealing little about what's happening in its atmosphere. Neptune's atmosphere contains bright clouds that appear and disappear over hours or days, making the planet seem active and dynamic. These clouds are made of methane ice crystals forming at high altitudes, where temperatures are cold enough for methane to freeze. They cast shadows on cloud layers below them, allowing scientists to calculate their altitude and movement. Some clouds move with incredible speed, blown by winds reaching 1,000 miles per hour in the upper atmosphere. The planet also shows dark spots, oval-shaped storms similar to Jupiter's Great Red Spot, but less permanent. The first dark spot, discovered by Voyager 2 in 1989, was about the size of Earth and accompanied by bright companion clouds nicknamed Scooter because they moved faster than the main storm. When Hubble Space Telescope looked for this storm 5 years later, it was gone, having dissipated completely. New dark spots have appeared in different locations, suggesting these storms form and decay on timescales of years, rather than persisting for centuries like Jupiter's storms. Neptune's internal heat plays a role in driving this atmospheric activity. The planet radiates about 2.5 times more energy than it receives from the Sun, heat left over from its formation still slowly escaping from the interior. This internal energy source powers the winds and storms, keeping the atmosphere turbulent despite receiving so little sunlight at its vast distance from the Sun. Mercury, closest to the Sun, receives about 10 times more sunlight per unit area than Earth. Neptune, 30 times farther out, receives about 900 times less. This variation affects everything: temperature, atmospheric dynamics, whether materials exist as solids, liquids, or gases. At Mercury's distance, water would instantly vaporize and be blown away by solar wind. At Neptune's distance, methane and even nitrogen can freeze solid. The habitable zone where liquid water can exist is surprisingly narrow, extending from about 90 million to 150 million miles from the Sun. Earth orbits at 93 million miles, safely within this zone. Venus at 67 million miles is too close, resulting in runaway greenhouse effect. Mars at 142 million miles is near the outer edge, cold enough that water can exist only as ice or briefly as vapor. But distance alone doesn't determine habitability. Moons of Jupiter and Saturn, far beyond the traditional habitable zone, may have liquid water oceans heated by tidal forces rather than sunlight. This expands our thinking about where life might exist, suggesting we should consider not just planets at the right distance from their star, but moons at any distance, if they have internal heat sources maintaining liquid water. Besides Earth, at least 6 other bodies in our solar system likely have liquid water: Europa, Ganymede, Callisto, Enceladus, Titan, and Ceres. Some have subsurface oceans, some have water mixed with ammonia or other compounds lowering its freezing point, and some have liquid water only in specific locations beneath ice shells. Combined, these subsurface oceans contain far more water than all of Earth's oceans. Europa alone might have twice Earth's total water volume, and Ganymede's ocean could be even larger. This water has been liquid for billions of years in some cases. Stable environments where chemistry could proceed, where complex molecules could form, where, possibly, life could emerge and persist. These oceans are isolated from space by ice shells, protecting them from radiation and maintaining stable conditions. They're heated not by sunlight, but by tidal forces and radioactive decay, energy sources that don't depend on proximity to the sun. This makes them fundamentally different from Earth's oceans, which are intimately connected to the atmosphere and powered by solar energy. Subsurface oceans are dark, cold near the ice shell, but possibly warm near the rocky seafloor, where hydrothermal vents might exist. Exploring them requires drilling through miles of ice, a significant technical challenge, but one within the realm of possibility with current or near-future technology. Titan's lakes are filled not with water, but with liquid methane and ethane, hydrocarbons that are gases on Earth, but liquids at Titan's frigid temperatures of -290 degrees Fahrenheit. These lakes, concentrated near the poles, range in size from small ponds to Kraken Mare, a sea larger than the Great Lakes combined. The liquid is incredibly pure, containing almost no dissolved solids, making it more transparent than any water on Earth. The shorelines show features similar to terrestrial coastlines, with bays, inlets, and river deltas where methane rivers deposit sediments carried from higher terrain. Some lakes show changes over time, appearing to evaporate during summer and refill during winter, demonstrating that Titan has a complete hydrological cycle like Earth's, but using methane instead of water. Rain falls from methane clouds, creating streams that carve valleys and flow into lakes. The lakes evaporate, returning methane to the atmosphere where it forms new clouds, completing the cycle. This makes Titan the only other body in our solar system with stable liquids on its surface, the only other place where you could see rain falling, rivers flowing, and lakes shimmering in the dim sunlight. The surface around the lakes shows features suggesting ancient shorelines at higher elevations, implying lake levels have changed over geological time, perhaps due to climate variations or changes in methane abundance in the atmosphere. Cryovolcanism, or ice volcanism, occurs when volatiles like water, ammonia, or methane erupt from the interior of icy bodies. Instead of molten rock, these volcanoes erupt slushy mixtures, or even liquids, at temperatures far below 0 Fahrenheit. Enceladus's geysers are a form of cryovolcanism, erupting water and ice particles from cracks in the South Polar region. Triton shows evidence of past cryovolcanic activity, with smooth plains suggesting material resurfaced the Moon relatively recently. Ceres has a mountain called Ahuna Mons that appears to be a cryovolcano, a dome of ice that pushed up through the crust, possibly erupting salty water that froze upon reaching the surface. These eruptions are driven by the same forces as conventional volcanism on Earth, internal heat and pressure, but the materials and temperatures are vastly different. Cryovolcanism helps explain why some icy moons have young surfaces despite being billions of years old. Fresh material erupting from the interior covers old, cratered terrain, creating smooth plains that look geologically recent. It also provides a mechanism for subsurface oceans to interact with the surface, allowing exchange of materials between the two regions. This exchange could deliver nutrients from the rocky core to the ocean, and could, in principle, allow any organisms in the ocean to reach the surface where future spacecraft might sample them. Water ice in the outer solar system exists at temperatures where it's as hard as granite. At -200 degrees Fahrenheit and below, water ice doesn't behave like the ice in your freezer. It becomes brittle and strong, capable of forming mountains and cliffs that don't flow or deform easily. Different forms of ice, called phases, exist under different temperature and pressure conditions. Ice on Europa and Ganymede might be ice I, the form familiar to us near the surface. But deeper down, under higher pressure, it could transform into ice III, ice Varg, or even ice Saskix, denser phases, where the crystalline structure is compressed. The deepest ice might be ice VII, where hydrogen atoms are arranged differently, creating ice that's dense and exotic. These different ice phases have different properties, affecting how heat and sound travel through them, how they respond to stress, and whether liquid water can exist at their boundaries. The transition zones between ice phases might be locations where melting occurs more easily, potentially creating pockets of liquid water at depths where we wouldn't normally expect them. Understanding these exotic ices is important for modelling the interiors of icy moons and predicting where subsurface oceans might exist and how they interact with the rocky cores below and the ice shells above. Impact craters on icy moons look different from craters on rocky bodies. When an object strikes ice at high speed, the impact melts and vaporizes the ice, creating a temporary crater. But ice behaves differently than rock over time. On rocky bodies, craters remain sharp and deep, almost indefinitely. On icy bodies, especially those with internal heat, the ice slowly flows over geological time, a process called viscous relaxation, gradually filling in craters and smoothing the surface. This means old craters on icy moons are shallow and subdued, while fresh craters are deep with sharp rims. By studying the shapes of craters, scientists can estimate how much internal heat a moon has and how active its geology is. Moons with many shallow craters, like Ganymede, have experienced enough internal heating to relax their craters over billions of years. Moons with sharp, deep craters, like Callisto, have remained cold and rigid, preserving their impact history in pristine detail. Some craters on icy moons show bright rays of fresh ice extending outward, material excavated from below the surface that hasn't yet darkened from radiation exposure. These rays can extend for hundreds of miles, creating striking patterns visible from space, connecting impacts that happened millions of years ago to features we can observe today. Beyond Neptune lies the scattered disk, a region where objects have highly elliptical orbits, taking them from near Neptune out to hundreds of astronomical units from the Sun. These objects were likely scattered into their current orbits by gravitational interactions with Neptune during the early solar system, when the giant planets were migrating to their current positions. The scattered disk merges with the Kuiper belt, making it difficult to distinguish where one region ends and the other begins. Some objects cross the boundary between regions during their orbits, spending part of their time in the Kuiper belt's orderly plane, and part of their time in the scattered disk's chaotic trajectories. Eris, one of the largest known dwarf planets, orbits in the scattered disk, taking about 560 years to complete one orbit. Its orbit is so elliptical that at closest approach, it comes within 38 astronomical units of the Sun, closer than Pluto at its farthest, while at its most distant, it reaches nearly 98 astronomical units, far beyond the Kuiper belt. This extreme ellipticity is characteristic of scattered disk objects, evidence of the gravitational chaos that placed them in these orbits billions of years ago. The Oort cloud is theorized to be a spherical shell of icy objects surrounding the solar system at distances between 5,000 and 100,000 astronomical units from the Sun. At those distances, the Sun would appear as just a bright star, barely distinguishable from other stars, providing almost no heat. Objects in the Oort cloud orbit so slowly that they take millions of years to complete a single orbit, moving at speeds measured in just a few feet per second. The Oort cloud has never been directly observed because its objects are too small and too distant to see with current telescopes. But we infer its existence from the orbits of long-period comets, those taking thousands or millions of years to orbit the Sun. These comets approach from all directions, not just from the ecliptic plane where planets orbit, suggesting they come from a spherical cloud rather than a flat disk. Occasionally, a passing star or gravitational perturbations from the galactic tide nudge an Oort cloud object, changing its orbit enough to send it falling inward toward the Sun. As it approaches and heats up, it becomes a comet, growing a coma and tail, making itself visible for the brief time it spends near the inner solar system, before retreating back into the cold and dark for eons. Comets are among the most primitive objects in our solar system, largely unchanged since forming 4.5 billion years ago. They contain ices, organic molecules, and dust grains that predate the Sun itself, materials that survived from the molecular cloud that collapsed to form the solar system. When we study comets, we're studying samples of the primordial material from which everything was built, preserved in a deep freeze for billions of years. Missions to comets have found amino acids, the building blocks of proteins and complex organic molecules, evidence that the chemistry needed for life is common in space, and may have been delivered to Earth by comets and asteroids during the early bombardment period. Some scientists believe Earth's water came primarily from comets, though recent measurements suggest asteroids might have been the main source instead, or perhaps a combination of both. Either way, comets represent a connection to our origins, carriers of materials that made life possible, visitors from the edge of the solar system, bringing gifts from the distant past every time they swing past the Sun. Gravity holds the solar system together, keeps planets in orbit, prevents the Sun from flying apart, and governs the motion of every object from tiny dust grains to massive planets. It's a simple force, always attractive, never repulsive, following an inverse square law where strength decreases with the square of the distance. Yet this simplicity creates incredible complexity when multiple objects interact. The gravitational dance between Jupiter's moons creates tidal heating that powers volcanoes and maintains subsurface oceans. The gravitational influence of Neptune shaped the Kuiper belt, clearing certain regions and concentrating objects in others. The gravitational pull of passing stars may occasionally disturb the Oort cloud, sending comets inward. Even galaxies influence each other through gravity over millions of light years, a force that shapes the universe at every scale. In our solar system, we see gravity's effects everywhere, from the rings of Saturn shaped by shepherd moons to the orbital resonances of Jupiter's moons that keep them in synchronized patterns. Gravity is patient and persistent, working over billions of years to organize chaos into order, creating the stable, predictable system we observe today. The solar wind is not a gentle breeze, but a torrent of charged particles streaming outward from the sun at speeds of 1 million miles per hour. This invisible river of protons and electrons flows constantly, carrying the sun's magnetic field into space, creating what we call the interplanetary magnetic field. The solar wind isn't uniform, but varies in density and speed, sometimes calm, sometimes gusting during solar storms, when flares or coronal mass ejections hurl billions of tons of plasma into space at even higher speeds. These storms can reach Earth in as little as 15 hours, compressing our magnetic field, creating spectacular auroras, and occasionally disrupting satellites and power grids. The solar wind shapes the magnetospheres of planets, carving out cavities in space where planetary magnetic fields dominate. For planets without magnetic fields, like Mars and Venus, the solar wind interacts directly with their upper atmospheres, slowly stripping away atmospheric particles over millions of years. This process likely transformed Mars from a world with thick atmosphere and liquid water into the cold, dry planet we see today. The solar wind also creates the ion tails of comets, pushing charged particles away from the sun, regardless of the comet's direction of motion. These tails can stretch for millions of miles, visible evidence of the solar wind's power, made manifest in glowing gas illuminated by sunlight. Earth's magnetic field is generated by the geodynamo, the motion of liquid iron and nickel in the outer core, about 1,800 miles beneath our feet. This churning metal acts like a vast electrical generator, creating currents that produce a magnetic field extending tens of thousands of miles into space. The field is not static, but changes over time, both in strength and direction. The magnetic North Pole wanders, currently moving from northern Canada towards Siberia at about 34 miles per year, faster than at any time in the past century. Every few 100,000 years, on average, the field reverses completely, north becoming south and south becoming north. These reversals are recorded in rocks, particularly in oceanic crust, where volcanic material crystallizes with magnetic minerals aligned to the field at the time of formation. By studying these magnetic stripes in rocks of different ages, scientists have mapped out the history of field reversals going back millions of years. The last reversal occurred about 770,000 years ago, and were overdue for another based on the average interval. During a reversal, the field doesn't disappear, but becomes complex and disorganized, possibly weakening enough to allow more cosmic rays to reach the surface. The transition takes a few thousand years, a blink in geological time, but long enough for life to adapt. Our field protects us not just from the solar wind, but from galactic cosmic rays, high-energy particles, from supernova explosions, and other violent events across the galaxy. Auroras occur when charged particles from the solar wind follow Earth's magnetic field lines down toward the poles, entering the upper atmosphere at altitudes between 60 and 200 miles. These particles, mostly electrons and protons, collide with oxygen and nitrogen atoms, transferring energy that causes the atoms to emit light. Oxygen produces green and red light depending on altitude, while nitrogen creates blue and purple hues. The most common auroras are green, caused by oxygen at lower altitudes, creating curtains of light that shimmer and dance, following the magnetic field lines. Red auroras occur higher up where oxygen is more dispersed, producing deeper, richer colours that are less common but more dramatic. The auroras are not static, but constantly changing, rippling and pulsing in response to variations in the solar wind. During major solar storms, auroras can be seen at much lower latitudes than usual, sometimes visible from the northern United States, or even farther south. In 1859, during the Carrington event, the largest recorded solar storm, auroras were visible as far south as the Caribbean, and the night sky was bright enough to read by in some locations. The lights occur simultaneously in both hemispheres, mirror images of each other, connected by the magnetic field lines threading through Earth's interior. Jupiter's auroras are far more powerful than Earth's, driven not primarily by the solar wind, but by material from Io's volcanoes. Sulfur and oxygen from Io's eruptions become ionized and trapped in Jupiter's magnetic field, forming a plasma torus around the planet. As Jupiter rotates, its magnetic field sweeps through this plasma, accelerating particles to incredible speeds before they crash into the planet's upper atmosphere near the poles, creating auroras that are almost always present, unlike Earth's, which appear only during active solar periods. These Jovian auroras emit not just visible light, but also intense ultraviolet and X-rays, radiation that would be dangerous to any spacecraft venturing too close. The auroras form ovals around each pole, sometimes hundreds or even thousands of miles across, bright enough to see through telescopes from Earth. Some of Jupiter's moons also create their own auroral footprints in Jupiter's atmosphere, spots where magnetic field lines connected to the moon's funnel particles downward. Io, Europa, and Ganymede each have their own footprint, glowing spots that move across Jupiter's face as the moon's orbit. These footprints are evidence of the complex electrical currents flowing between Jupiter and its moons, invisible connections made visible through light. Solar flares are sudden explosions on the sun's surface, releasing as much energy as millions of nuclear bombs in just minutes. They occur when magnetic field lines become tangled and stressed, suddenly snapping and reconnecting in a process called magnetic reconnection, converting magnetic energy into heat, light, and kinetic energy. Flares are classified by their X-ray brightness, from A class, the smallest, through B, C, M, and finally X class, the largest. A major X-class flare releases the energy equivalent of billions of megatons of TNT, heating plasma to tens of millions of degrees and accelerating particles to nearly the speed of light. These energetic particles arrive at Earth within minutes, potentially endangering astronauts and airline passengers at high altitudes where the atmosphere provides less shielding. The light from flares spans the spectrum, from radio waves through visible light to X-rays and gamma rays. The most intense radiation is absorbed by Earth's atmosphere, which is fortunate because it would be harmful to life on the surface. Flares often accompany coronal mass ejections, massive bubbles of plasma hurled into space, though not all flares produce ejections, and not all ejections are associated with flares. When a large coronal mass ejection happens to be aimed at Earth, it takes 1 to 3 days to arrive, giving us time to prepare by shutting down sensitive systems and warning astronauts to take shelter. The solar cycle is an approximately 11-year period during which the sun's activity waxes and wanes. During solar maximum, the sun is covered with sunspots, dark regions where strong magnetic fields inhibit convection and cool the surface. Flares and coronal mass ejections are common, and the sun's output of X-rays and ultraviolet light increases. During solar minimum, the surface is often spotless for weeks at a time. Activity diminishes, and the sun appears calm. This cycle has been tracked since the early 1600s, when Galileo and other astronomers first observed sunspots through telescopes. The cycle is not perfectly regular, sometimes lasting as short as 9 years, or as long as 14, and the intensity varies considerably from one cycle to the next. Some cycles are very active with numerous large flares, while others are relatively quiet. There have been periods in history when the cycle seemed to stop altogether. The Maunder minimum, lasting from 1645 to 1715, was a 70-year period when sunspots became extremely rare, and the solar cycle seemed to disappear. This period coincided with the Little Ice Age in Europe, a time of unusually cold winters, though whether the two are causally connected remains debated. The solar cycle is driven by the sun's magnetic field, which reverses polarity every 11 years, meaning the full magnetic cycle is actually 22 years long. The solar corona is the sun's outer atmosphere, a region of extremely hot but tenuous plasma extending millions of miles into space. Despite being farther from the sun's core, the corona is paradoxically much hotter than the surface, reaching temperatures of 1 to 3 million degrees Fahrenheit compared to the surface's 10,000 degrees. This has puzzled scientists for decades. The leading theory is that magnetic field lines threading through the corona carry energy upward from below, and when these field lines reconnect, they release energy as heat. Another possibility is that waves propagating through the plasma deposit their energy as they travel outward, heating the corona through friction and turbulence. The corona is visible during total solar eclipses, when the moon blocks the bright surface and reveals the faint, wispy structures surrounding the sun. These structures follow magnetic field lines, creating loops, arches, and streamers that change shape over days and weeks. Some regions of the corona are darker, called coronal holes, where magnetic field lines are open to space rather than looping back to the surface. These holes allow solar wind to escape more easily, creating high-speed streams that can buffet Earth's magnetic field when they happen to be aimed our direction. The sun's core, where fusion occurs, is surrounded by the radiative zone, extending about 2/3 of the way to the surface. In this region, energy moves outward through radiation, photons being absorbed and re-emitted countless times as they slowly work their way through the dense plasma. A single photon can take over 100,000 years to travel from the core to the top of the radiative zone, constantly scattering and changing direction. Above the radiative zone lies the convective zone, where energy is transported by moving plasma rather than radiation. Hot plasma rises, cools near the surface, and sinks back down, creating convection cells, visible on the sun's surface as granulation. Each granule is about 600 miles across and lasts about 10 minutes before the pattern shifts and new granules form. Larger convection, cells called supergranules, about 20,000 miles across, last about a day. These flowing patterns transport energy, but also help generate and organize the sun's magnetic field through a dynamo process similar to Earth's but far more complex. The surface, called the photosphere, is where light finally escapes into space, the layer we see when we look at the Sun. It's only about 300 miles thick, a thin shell marking the transition from opaque interior to transparent space. The chromosphere is a thin layer above the photosphere, about 1,500 miles thick, where temperature actually increases with altitude, rising from 7,500 degrees at the bottom to about 50,000 degrees at the top. It's normally invisible, outshone by the bright photosphere, but during total solar eclipses, just after the photosphere is blocked, the chromosphere appears as a thin reddish ring around the Moon's silhouette. That red color comes from hydrogen alpha emission, hydrogen atoms excited by the intense energy environment releasing photons at a specific wavelength that appears red to our eyes. The chromosphere is home to spicules, jet-like eruptions of plasma shooting upward at tens of thousands of miles per hour, reaching heights of 6,000 miles before falling back down. These spicules are constantly forming and fading, covering the Sun's surface in a forest of rising and falling plasma jets, each lasting just minutes. They may play a role in heating the corona, carrying energy upward from the chromosphere into the higher atmosphere. Prominences also form in the chromosphere, large loops of plasma suspended above the surface by magnetic fields, sometimes remaining stable for weeks before erupting into space or falling back to the surface in a shower of glowing material. The Sun is a G-type main sequence star, often called a yellow dwarf, though it actually appears white from space. It's average in almost every way, middle-aged, middle-sized, middle temperature, not particularly bright or dim compared to other stars. About 3/4 of all stars in our galaxy are red dwarfs, smaller and cooler than the Sun, while only a small fraction are larger and brighter. This ordinariness is actually fortunate. More massive stars burn through their fuel much faster, lasting only millions of years rather than billions. Not enough time for life to develop on any orbiting planets. Red dwarfs last trillions of years, but are prone to violent flares that could sterilize nearby planets. The Sun's moderate nature, its stability over billions of years, made it possible for life to arise and evolve on Earth without being disrupted by extreme stellar behavior. The Sun formed from a molecular cloud about 4.6 billion years ago, along with countless other stars, part of a stellar nursery that has since dispersed. Its siblings are now scattered throughout the galaxy, indistinguishable among the billions of other stars. By studying the Sun, we learn about stars in general, understanding stellar physics, magnetic fields, energy generation, and stellar evolution, knowledge applicable to stars across the universe. Nuclear fusion in the Sun's core combines 4 hydrogen nuclei into one helium nucleus, releasing energy in the form of gamma-ray photons. This process, called the proton-proton chain, is incredibly inefficient at any individual attempt. The probability of any given collision resulting in fusion is absurdly low. But the Sun's core contains so many hydrogen atoms, and collisions happen so frequently that enough fusion occurs to power the Sun's luminosity. Every second, the Sun converts about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons become energy through Einstein's equation E equals mc², the mass converted into the light and heat that sustain us. The helium produced by fusion accumulates in the core, gradually increasing the core's density and temperature. Eventually, billions of years from now, the core will be mostly helium with no hydrogen left to fuse. At that point, the core will contract and heat up until it reaches temperatures high enough to fuse helium into carbon and oxygen, marking the Sun's transition from main sequence star to red giant. This process, helium fusion, releases even more energy than hydrogen fusion, causing the Sun to expand dramatically. As the Sun becomes a red giant, it will swell to perhaps 100 times its current diameter, possibly extending past Earth's orbit. The surface temperature will drop to about half its current value, making it appear reddish rather than yellow. But the total luminosity will increase by thousands of times because of the vastly larger surface area. Mercury will certainly be consumed, vaporized, and absorbed into the expanding solar atmosphere. Venus will likely be engulfed as well. Earth's fate is less certain. Some calculations suggest Earth's orbit will expand outward as the Sun loses mass, keeping it just beyond the reach of the solar atmosphere. Others suggest Earth will be consumed, or, even if it survives, will be roasted by the intense heat, oceans boiling away, atmosphere stripped, leaving a scorched, lifeless rock. Mars, farther out, might become warm enough for liquid water briefly, though it will lack the thick atmosphere needed to maintain it for long. The moons of Jupiter and Saturn will receive more heat, possibly making places like Europa and Titan more hospitable, though only temporarily. The red giant phase will last about 1 billion years, during which the Sun will pulse and pulsate, shedding mass through stellar winds and possibly through more dramatic events. Eventually, the helium in the core will be exhausted, and without fusion to support it, the core will contract again, while the outer layers expand even more. The outer layers will drift away, forming a planetary nebula, a beautiful shell of gas expanding into space, illuminated by the hot core left behind. This nebula, despite its name, has nothing to do with planets, but was named by early astronomers who thought these objects looked like planets through their telescopes. Planetary nebulae come in many shapes, sometimes spherical, sometimes bipolar with 2 lobes, sometimes more complex structures, depending on the star's rotation, magnetic fields, and whether it had a companion star. The Sun's planetary nebula will glow for about 10,000 years, gradually fading as it expands and thins, eventually dissipating into the interstellar medium, adding its material to the reservoir from which future stars and planets will form. The core left behind will be a white dwarf, a star roughly the size of Earth, but containing about half the Sun's current mass, with density so high that a teaspoon of white dwarf material would weigh several tons. The white dwarf will be hot initially, over 100,000 degrees at the surface, but with no fusion occurring, it will slowly cool over trillions of years, fading from white to yellow to red to eventually becoming a black dwarf, a cold, dark remnant that no longer emits significant light. The universe is not old enough for any black dwarfs to exist yet. All white dwarfs are still cooling. Planetary migration is the process by which planets change their orbits over time, moving inward or outward from their star. This was once considered impossible, because planetary orbits were thought to be stable for billions of years. But observations of exoplanets have revealed that migration is common, perhaps even typical. Hot Jupiters, massive planets orbiting very close to their stars, could not have formed in those locations because temperatures were too high for gas giants to accumulate material. They must have formed farther out, and migrated inward, either through gravitational interactions with the protoplanetary disk or through interactions with other planets. Our own solar system may have experienced migration. The NICE model, named after the city in France where it was developed, suggests that Jupiter, Saturn, Uranus, and Neptune formed in more compact orbits than they currently occupy. Gravitational interactions between them, particularly a close encounter between Jupiter and Saturn, caused Neptune and Uranus to migrate outward, scattering objects in what was then a dense disk beyond their orbits. This migration triggered the late heavy bombardment about 4 billion years ago, when a sudden increase in asteroid impacts struck the inner planets, creating many of the craters we see on the Moon and Mercury today. Evidence for this model comes from the current orbits of Jupiter and Saturn, which are in a specific mathematical relationship called a resonance that could have formed during migration, and from the structure of the Kuiper belt, which shows signs of having been disrupted by Neptune's outward movement. Water in the inner solar system came from somewhere. Earth formed at a temperature too high for water ice to condense directly, yet we have vast oceans. The water must have been delivered after the planet cooled, brought by asteroids and comets from the outer solar system. Asteroids from the outer main belt, beyond about 2.7 astronomical units, contain water-bearing minerals and could have provided much of Earth's water. Comets were once thought to be the primary source, but measurements of deuterium to hydrogen ratios in comets don't always match Earth's water, suggesting asteroids played a larger role. Venus likely received similar deliveries early in its history, but lost its water when the atmosphere became dominated by carbon dioxide and a runaway greenhouse effect developed. Mars also received water, but couldn't hold on to it after losing its magnetic field and most of its atmosphere. The Moon, too small to hold an atmosphere and with no magnetic field, lost any water delivered to its surface through impacts, though water ice persists in permanently shadowed polar craters. The delivery of water was not gentle but violent. Countless impacts over hundreds of millions of years, each one bringing a small fraction of the total, gradually building up the reservoirs we see today. This water brought not just H2O, but dissolved salts, organic compounds, and possibly even prebiotic molecules that contributed to the chemistry leading to life. Atmospheric composition varies dramatically across the solar system. The gas giants, Jupiter and Saturn, retained their primordial atmospheres, mostly hydrogen and helium, the lightest elements. They were massive enough and formed early enough to capture these gases directly from the solar nebula before the young sun's radiation cleared it away. The ice giants, Uranus and Neptune, have atmospheres rich in water, ammonia, and methane, in addition to hydrogen and helium, reflecting their formation farther from the sun, where these compounds could condense into ices. The rocky planets have atmospheres of secondary origin, produced by volcanic outgassing after the planets formed, not captured from the original nebula. Earth's atmosphere evolved through biological processes. Mars lost most of its original atmosphere, and Venus's atmosphere became dominated by carbon dioxide from volcanic activity, with no mechanism to remove it. Titan has a thick nitrogen atmosphere with methane, possibly maintained by cryovolcanism, bringing volatiles from the interior. Triton has a thin atmosphere of nitrogen and methane maintained by seasonal sublimation of surface ices. The diversity reflects different formation conditions, different masses affecting what gases can be retained, and different evolutionary histories involving volcanism, impacts, biological processes, and solar radiation. Dust devils on Mars are whirlwinds caused by solar heating of the surface, creating convection currents in the thin atmosphere. These devils can be enormous, over 6 miles tall, dwarfing any on Earth, but they're much weaker because the atmosphere is so thin. Spacecraft have photographed their shadows cast on the surface, dark streaks showing their paths. Occasionally, dust devils pass directly over rovers, darkening the sky and pelting the instruments with dust, events recorded in detail by cameras and sensors. Mars also experiences global dust storms that can envelop the entire planet, lasting for months and making the surface invisible from orbit. These storms occur roughly every decade during southern summer when Mars is closest to the Sun. The extra heating drives winds that lift dust, and once enough dust is suspended, it absorbs sunlight and heats the atmosphere further, driving stronger winds in a feedback loop that sustains the storm. Eventually, the dust settles, taking months to clear completely. During the 2018 global dust storm, the Opportunity rover lost power when sunlight couldn't reach its solar panels through the dust-filled atmosphere, ending its mission after 14 years of operation. Venus's atmosphere rotates much faster than the planet itself, a phenomenon called superrotation. The planet takes 243 days to spin once, but the upper atmosphere whips around in just 4 days, creating winds exceeding 200 miles per hour at cloud level. This means the atmosphere circles the planet over 60 times for every one rotation of the surface. Driven by mechanisms scientists are still working to understand fully. The leading theory involves solar heating at the equator, creating rising air that moves poleward at high altitude, sinks near the poles, and returns towards the equator at lower altitude, creating circulation cells. The rotation of the planet deflects these flows, and conservation of angular momentum causes them to speed up as they converge toward the axis, creating the superrotation. The atmosphere also shows a strange Y-shaped pattern in the clouds when viewed in ultraviolet light, a feature that rotates with the 4-day period, arms extending from the equator toward the poles. This pattern is caused by variations in the concentration of sulfur dioxide and other UV-absorbing compounds, and it changes shape over days and weeks, suggesting complex dynamics in the upper atmosphere that remain mysterious despite multiple missions studying Venus. On Earth, ocean currents and atmospheric circulation transport heat from the equator toward the poles, moderating temperature differences and preventing extreme variations. On planets without this heat redistribution, day-night and equator pole temperature differences would be much more severe. Mars has only atmosphere, no oceans, so heat transport is less efficient, contributing to the large temperature swings between day and night and between seasons. Venus, despite its thick atmosphere and superrotation, shows surprisingly little temperature variation from equator to poles or from day to night. The dense atmosphere and strong winds distribute heat so effectively that the surface is nearly the same temperature everywhere, a testament to how efficiently a thick atmosphere can transport energy. Titan also shows relatively uniform temperatures despite having a thick atmosphere, with only a few degrees difference between equator and poles. This uniformity is partly due to the atmosphere's opacity, which prevents much solar heating from reaching the surface, and partly due to atmospheric circulation, driven by the small temperature differences that do exist. The giant planets, with no solid surfaces and fast rotation, show pronounced banding, alternating zones of different temperatures and wind speeds, with storm systems that can persist for decades or centuries, demonstrating that heat transport on these worlds follows different rules than on rocky planets. Meteoroids, small rocky or metallic objects in space, become meteors when they enter an atmosphere, heating up from friction until they glow, creating streaks of light across the sky. Most burn up completely, never reaching the surface, their energy dissipated as heat and light. Those that survive to hit the ground become meteorites. Earth's atmosphere protects us from countless small meteoroids that would otherwise sandblast the surface. The Moon, with no atmosphere, has a surface heavily pockmarked by impacts from even tiny particles. Over billions of years, this micrometeorite bombardment has ground up the surface layer into a fine powder called regolith, several feet thick in places. Mars has a thin atmosphere that provides some protection, but not as much as Earth's. Many meteoroids reach the surface, and the planet is peppered with craters of all sizes. Spacecraft orbiting Mars have occasionally detected fresh impact craters that weren't present in earlier images, evidence that impacts occur frequently enough to observe over the durations of a mission. These impacts throw up clouds of dust visible from orbit and create blast zones where the surface is disturbed for hundreds of feet around the crater. By studying the size and frequency of craters, scientists can estimate how often objects of different sizes hit planetary surfaces, helping us understand the bombardment rate throughout the solar system's history. Meteorites found on Earth include pieces of the Moon, Mars, and asteroids, ejected by large impacts and eventually falling to our planet after spending millions of years drifting through space. Lunar meteorites are identified by their composition matching samples returned by Apollo missions. Martian meteorites are identified by trapped gases in glass formed during the impact ejection, gases matching the composition of Mars's atmosphere measured by landers. These meteorites provide samples of other worlds without the need for expensive sample return missions. Studying them reveals details about the geology, age, and history of their parent bodies. Some Martian meteorites show evidence of having been exposed to liquid water, with minerals that form only in water's presence, supporting the idea that Mars once had a wetter climate. One meteorite, ALH 84001, sparked controversy when scientists announced they had found structures that might be fossilized Martian microbes. The claim remains disputed, with most scientists attributing the structures to non-biological processes. But it highlighted the possibility that meteorites could carry evidence of life from one planet to another, a concept called panspermia. Dust from comets and asteroids spreads throughout the inner solar system, creating the zodiacal light, a faint glow visible from dark locations after sunset or before sunrise. This light is sunlight reflecting off countless tiny particles orbiting the sun in a disk aligned with the ecliptic plane. From Earth, it appears as a triangular glow extending along the zodiac. Constellations, hence the name. The dust comes from comets shedding material as they approach the sun, and from asteroid collisions producing fragments. This dust slowly spirals inward toward the Sun, drawn by radiation pressure and the Poynting-Robertson effect, eventually falling into the Sun or being pushed out of the solar system by solar radiation. The dust is constantly replenished, so the zodiacal light has been visible for as long as comets and asteroids have been active. Spacecraft traveling through the inner solar system must contend with this dust, which can damage solar panels and instruments through high-speed impacts. The dust is sparse enough that most particles are smaller than sand grains, but at orbital speeds of tens of thousands of miles per hour, even tiny particles carry significant energy. The solar system has a background radio emission called the auroral kilometric radiation, produced by Earth's auroras when accelerated electrons spiral along magnetic field lines and emit radio waves. This radiation is strongest at frequencies around a few hundred kilohertz and is detectable from spacecraft, but not from Earth's surface, because our ionosphere blocks these frequencies. Jupiter also produces intense radio emissions, called decametric radiation, from its auroras and magnetosphere, strong enough to be detected by amateur radio enthusiasts on Earth with relatively simple equipment. These bursts of radio noise come and go as Jupiter rotates and as Io passes through certain positions in its orbit, affecting the magnetic field and triggering emissions. Saturn also emits radio waves, though weaker than Jupiter's, associated with its auroral regions and magnetospheric dynamics. These natural radio emissions were puzzling when first detected, because they implied electrical currents and magnetic processes far more powerful than anything on Earth. Understanding them required new theories about plasma physics and magnetic reconnection, expanding our knowledge of how ionized gases behave in space environments. The interplanetary medium contains a thin gas, about 5 particles per cubic centimeter in the inner solar system, mostly hydrogen and helium from the solar wind. This density is far lower than the best vacuums we can create on Earth. Yet, over the vast distances of the solar system, this gas has effects. It scatters light, contributes to the zodiacal light, and interacts with magnetic fields. In the outer solar system, the density drops even lower, approaching the density of interstellar space. The boundary between the solar wind and interstellar medium is called the heliopause, a region where the outward pressure of the solar wind balances the inward pressure of the interstellar medium. The Voyager spacecraft crossed this boundary in 2012, Voyager 1, and 2018, Voyager 2, detecting sudden changes in particle densities and magnetic field orientation, confirming they had left the heliosphere and entered the space between stars. This transition is not a sharp edge, but a complex boundary layer called the helios sheath, where turbulence and magnetic reconnection create a chaotic environment. Beyond the heliopause, the Voyagers are in interstellar space, but still gravitationally bound to the Sun, still technically within the solar system, even if they've left its protective bubble. Orbital mechanics require careful planning to move from one planet to another efficiently. You can't simply point a spacecraft toward your destination and fire the engines. Orbits are ellipses, and transferring from one orbit to another requires applying velocity changes at specific points. The most fuel-efficient transfer is called a Hohmann transfer orbit, an ellipse that touches both the starting orbit and destination orbit at opposite ends. Spacecraft fire engines to increase speed, raising their orbit into an ellipse, then fire again at the far end to circularize at the destination. This takes time: 6 months to reach Mars from Earth, 2.5 years to reach Jupiter, decades to reach the outer planets. To save time and fuel, mission planners use gravity assists, flying close to planets and using their gravity to change speed and direction. Voyager 2 used gravity assists at Jupiter, Saturn, Uranus, and Neptune, a trajectory that would have been impossible without these planetary flybys. Each encounter bent the spacecraft's path and increased its speed, allowing it to reach Neptune in 12 years, rather than the 30 years a direct flight would have required. Planning these trajectories is an art and a science, requiring precise knowledge of planetary positions and careful calculation of approach angles and distances. Lagrange points are positions where the gravitational forces of two large objects, such as the Sun and Earth, balance with the centrifugal force felt by a smaller object orbiting with them. There are 5 Lagrange points in any two-body system. L1, between the Sun and Earth, is where spacecraft can orbit while always seeing the Sun, useful for solar observation missions. L2, beyond Earth on the opposite side from the Sun, is where spacecraft can orbit in Earth's shadow, staying cold, ideal for infrared telescopes that need to be cooled to observe faint heat signatures from distant objects. The James Webb Space Telescope orbits at L2, taking advantage of this stable thermal environment. L3 is on the opposite side of the Sun from Earth, never visible from our planet, a popular location in science fiction for hidden planets, but not particularly useful in reality because it's unstable and requires frequent corrections to maintain position. L4 and L5 are 60 degrees ahead and behind Earth in its orbit, forming equilateral triangles with Earth and the Sun. These points are more stable and collect dust and asteroids, though none large enough to be easily visible. Spacecraft can orbit these points with minimal fuel expenditure, making them attractive for future space infrastructure. Mars has been the focus of exploration for decades, with dozens of missions sent to orbit, land on, or rove across its surface. This interest stems from its proximity, making it the easiest planet to reach with current technology, and from evidence that it once had conditions suitable for life. Future missions aim to return samples to Earth, allowing detailed analysis in laboratories with equipment far more sophisticated than can be sent to Mars. These samples will help answer questions about past habitability and whether life ever emerged there. Human missions to Mars are being planned by space agencies and private companies, though the challenges are significant. The journey takes 6 to 9 months each way. Astronauts would need to wait on Mars for the planets to realign before returning, a total mission duration of at least 2 years, possibly longer. Radiation exposure during the journey and on the surface is a major concern, as are the physiological effects of reduced gravity. Mars's gravity is 38% of Earth's, strong enough to walk normally, but weak enough that long-term effects on bones and muscles are unknown. Creating habitats, producing oxygen and water, growing food, and generating power all require technologies that are being developed but not yet proven at the scale needed for long-duration missions. Europa, with its subsurface ocean, is a prime candidate for finding life beyond Earth. Future missions plan to orbit Jupiter, making repeated flybys of Europa, mapping the ice shell's thickness, measuring the ocean's depth and composition, and searching for plumes like those on Enceladus, where material from the ocean erupts into space. One mission concept includes a lander that would analyze surface ice for organic molecules and signs of biological activity. Another, more ambitious, involves a probe that would melt through the ice shell and deploy a submarine to explore the ocean directly, searching for life in the dark waters beneath. Such a mission is decades away, requiring technologies not yet developed, but it's being seriously considered because the science return would be transformative. Enceladus is another target, its geysers offering easier access to subsurface material without needing to drill through ice. A spacecraft could fly through the plumes repeatedly, collecting samples and analyzing them for complex organic molecules, salts, and other chemicals that would indicate whether the ocean is habitable and possibly inhabited. Space exploration is expensive and time-consuming, requiring investments spanning decades from concept to launch to data return. No single nation can easily afford the most ambitious missions, leading to international partnerships where countries contribute instruments, launch vehicles, or expertise. The International Space Station is the most visible example, a laboratory in orbit assembled and operated by the United States, Russia, Europe, Japan, and Canada, with contributions from other countries. Mars sample return is being planned as a joint mission between NASA and the European Space Agency, with each agency contributing critical components. These partnerships allow more ambitious projects, but also introduce complexity in coordination and decision-making. Private companies are increasingly involved in space exploration, launching satellites, resupplying the space station, and planning their own missions to the Moon and Mars. This public-private collaboration is expanding what's possible, bringing new ideas and capabilities to space exploration, while governments focus on science and exploration that doesn't have immediate commercial returns. Every discovery in the solar system adds to our understanding of how planets form, how life emerges, and whether we are alone. Finding life elsewhere, even microbial life in Mars's subsurface or Europa's ocean, would revolutionize biology and philosophy, proving that life is not unique to Earth, but arises wherever conditions allow. Not finding life despite thorough searching would also be informative, suggesting that life is rare and Earth is special, making our responsibility to preserve it even greater. The search for life is one motivator for exploration, but not the only one. Understanding planetary processes, from volcanism on Io to weather on Saturn, helps us understand Earth by comparison. Studying impact craters and bombardment history tells us about the violent early solar system and the risks we still face from asteroid impacts. Mapping resources on the Moon, Mars, and asteroids informs future plans for utilizing space materials, rather than launching everything from Earth's deep gravity well. The knowledge gained is cumulative, each mission building on previous ones, slowly filling in our picture of the solar system as a complex, dynamic place. Saturn's rings, backlit by the sun, glow with ethereal light, individual particles catching sunlight and creating a luminous disk. Jupiter's great red spot swirls in ever-changing patterns, a storm larger than our planet raging for centuries. Earth rising above the Moon's horizon, a blue and white marble suspended in the blackness of space. One of the most iconic images ever captured, reminding us of our planet's fragility and beauty. The geysers of Enceladus shooting into space, backlit by Saturn, creating a spectacle of ice and light. the orange haze of Titan's atmosphere, hiding a landscape that might look familiar if we could see through the clouds. The rust-coloured sands of Mars under a butterscotch sky, strange and yet somehow inviting, a world that might one day host human footprints. These images, captured by robotic explorers, bring distant worlds into our awareness, making the abstract real, transforming statistics and orbital parameters into places we can imagine visiting, landscapes that feel almost tangible despite being millions of miles away. Every atom in your body was forged in stars, scattered through space when those stars died, gathered into the cloud that formed the sun and planets. You are made of stardust in the most literal sense, cosmic recycling that makes you intimately connected to the universe. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces and supernova explosions, then wandered through space for millions of years before becoming part of Earth, part of you. We orbit a star that is ordinary, yet extraordinary in its stability, its longevity, its placement in a galaxy at a time when planets could form and life could emerge. We share this solar system with giant worlds and tiny moons, with asteroids that remember the beginning and comets that visit from the edge, with dust and radiation and invisible magnetic fields, all moving in patterns set billions of years ago, all connected through gravity's embrace. And so, here we are, having journeyed from the sun's core to the edge of its influence, from the scorched rocks nearest our star to the frozen wanderers at the boundary of night. You've travelled billions of miles tonight without leaving your resting place. You've stood on worlds of ice and fire, watched storms that dwarf our planet, felt the pull of gravity from giants and the whisper of solar wind at the edge of everything we know. This solar system, this collection of worlds spinning through darkness, is not separate from you. You are part of it, made from its materials, warmed by its star, protected by magnetic fields and atmospheres that have shielded life for billions of years. Every breath you take contains oxygen made in dying stars. Every thought you think is powered by atoms that once drifted through interstellar clouds. Tomorrow, when you look up and see that bright point of light we call Venus, or the reddish glow of Mars, or the steady shine of Jupiter, remember that they are not just lights in the sky, but worlds, places with landscapes and weather and histories as complex as Earth's. They are neighbours in this cosmic arrangement, sharing the same sun, following the same laws, part of the same ancient dance. The solar system continues without pause, planets orbiting, moons circling, asteroids tumbling, all moving along paths determined when everything began. This grand choreography will continue long after we're gone, a stability that spans eons, a permanence that makes our individual concerns feel small and yet precious because we get to witness it, to understand it, to marvel at how it all fits together. Rest now. Let your mind settle like dust falling through the stillness of space. Let your breathing slow like the patient orbits of distant worlds. Let the worries of the day drift away like solar wind dispersing into the dark. You are here, in this moment, part of a system billions of years old, living on a world perfectly positioned, breathing air made possible by life itself, thinking thoughts made possible by atoms from stars that died before the sun was born. And that is enough. That is more than enough. That is everything. Sleep well. The solar system will keep turning. The sun will keep shining. And you will wake to find yourself still here, still part of this beautiful, improbable arrangement we call home. Good night,